That fast algorithm for sorting that we're going to look at is called merge sort. And it's a very simple method. We take the array that we need to sort and we divide it into two halves. And then what we do is recursively, we resort each of the halves. So now we have two sorted subarrays, half the size of the original one. And then we merge the two halves together to make a sorted whole. That's a merge sort. It was invented actually by one of the pioneers of computing, John von Neumann. We'll talk about him later on in the course. The early focus when computers were first being built was on numerical calculations. But what John von Neumann did was invented merge sort really as a test to see how the computer would work on other tasks. And merge sort definitely has stood the tests of time. So let's look in more detail at how merge sort works. First, what we need to do is implement the merge. Now, it turns out that merging is a little more complicated than you might think. One thing that is hard to do is to merge an array in place. If we have our two sorted subarrays, to do it within the same array is a little tricky. It's very tricky, in fact. So instead what we're going to do is take an auxiliary array, an extra array, to put the results into. And then when we've got the merge done, then we'll copy it back. So this is a flaw of merge sort. There's other methods that don't have this characteristic that you need an extra array, and you can learn about those in an algorithm course. So we're going to keep an array called aux, that's an extra array, and then we're going to write this program merge that behaves as if it did the merge in place. So that is, we take our array, we take low, mid, and high, and it's going to say low, mid, again using our notation doesn't include mid, and then mid, high, and notation doesn't include I. And then we're going to put the result into aux and then merge it back. And then copy it back as if the merge happened in place. So that sets up our indices. All we do is maintain one pointer I that points to the low part of the array, another pointer j that points to the high part of the array. We compute the number of things that we're going to have to do, which is just high minus low, and then k is an index into aux, the result. So if we get to a point where the low part is exhausted, we copy over, this is an edge case that we'll talk about later, we just copy over, but the main part of this is to check the element at j against the element at j, at I, and then move the smaller one into aux and increment that pointer. So if j is less, then we move the one at j. If I is less, we move the one at I. And then we copy it back into A. So let's look at how this works. So I starts out pointing to Alice, and j starts out pointing to Bob. So Alice is smaller, so we move that one over. And now Bob's smaller, so we move that one over. Each time k gets the aux of k gets the next element that belongs there, but all we're doing each time is one comparison, picking the smaller from the two subarrays. So now Eve is smaller, so that's going to go, and Frank is smaller, so that's going to go. And the one that we move, that's the index that we increment. It's quite a simple process, and you look at this code, you'll understand how it works. And then eventually one of the arrays exhausts, and that's what the two first conditions in the if statement are for. It's just to move everything from the other one over. So that's merge. And then we copy it back, so the effect is as if we did it in place, but we have that auxiliary array. Now, given that merge, then merge sort is a recursive program that uses that abstract in place merge to get the job done. And so There's the merge method, and the aux is a global array that everybody can refer to. And we do that so that we, within our sort method, we allocate that array just once, and then call a recursive method that takes indices, just like binary search did. And here's the recursive method. It sorts the subarray of an array A between index low and high, again, not including A of high using our standard notation. So we compute n. If it's less than one element, we return. Otherwise, we compute our midpoint, sort the half with the smallest indices, sort the half with the larger indices, and then merge. And so all of that setup for the merge is to make this code so transparent. Divide the array in halves, sort the two halves, merge the two halves to make a sorted whole. That's merge sort. And we'll use the same test client as for insertion, which is just read strings off standard input and then sort them. And again, this is going to sort for our example, and we'll do a trace in just a minute. So that's merge sort. Pretty straightforward implementation, although you have to make sure that you get the auxiliary array part right. If you put that within the recursive routine, it would be too slow. Okay, so let's look at how it works dynamically. So what do we have to do to sort that array? We have to first sort the first half. What do we have to do to that one? We have to first sort the first half of that one. To sort that one, we have to sort Wendy and Alice. And finally, we get down to an array of size 1 that can be considered sorted. So then we have to consider the other size, array of size 1, and now those are considered sorted. And they are sorted, they're just 1. And now we merge those two sorted subfiles together to get Alice and Wendy in the proper order. Now we do the second half of the array of size 4 at the beginning, and then we have Dave and Walter, and they're already in order. Now we have two subarrays of size 2 that we can merge together to get the first 4 elements in sorted order. Now we're finished with the first half of the array of size 8 at the beginning, and we can work on the second half in the same way. So file of size 2, second file of size 2, merge those together to get 2 subfiles of size 4, and now we can merge those together to get the first 8 elements sorted. Now we do the same thing for the second half of the array, and you can follow through the dynamics of merge sort. Now we have the one of size 4 sorted. We do the second one of size 4, same way. Now merge together those two 4s to get an 8, and now we have the two 8s, and we can merge those together to get the entire array sorted. That's merge sort. Let's do the analysis. So to make it even simpler, we'll count just the number of times a string moves from one array to the other. The comparisons is a little more complicated to analyze, but this is quite simple. And again, we'll do the analysis for when n is the power of 2 this time. And that's now if big N equals 2 to the little n is exactly log base 2 of big N. And we start out with an array of size 2 to the little n, and we split it in half. We have 2 arrays of size 2 to the little n minus 1. Divide 2 to the n by 2, you get 2 to the little n minus 1. And split all those in half, you get 4 subarrays of size 2 to the n minus 2. Now, if you look down at the bottom, it does the calculation of how many data moves do you do. Well, the merge, for at the beginning, you do a merge of 2 things of size n over 2 into the auxiliary array, so that's n data moves, and then you move them back. So it's 2n data moves. And that's true for each subarray, but if we do it for 2 subarrays, then it's going to be 2n data moves total for both of those subarrays. And going all that way, every time, the total number of data moves for all arrays of that size is going to be 2n. So that means the total number of data moves is 2n natural log n, because we have n phases that's counted by the subarray size, little n phases, which is log of big N. So the total number is 2n natural log of big N. That's a quick way to see that the running time of merge sort is proportional to n log n. And again, this basic argument works even when n is not a power of 2, and you can learn more detail about that in a course on algorithms. That's our mathematical model, and again, we want to do empirical tests to check the mathematical model, again, using the same model that we use for insertion sort. And now it takes just a second to do 1,000,000, 2 seconds to do 2,000,000, and then in 16,000,000, 20 seconds, you could do 1,000,000,000 in not too much time, in a few minutes. 20 minutes to do sort 1,000,000,000 items, which is definitely fast enough for Alice and Bob type applications. And it confirms the hypothesis that the order of growth is either linear or n log n. And our math model said n log n, and this confirms that. So that's a fast sorting method. Now, sorting's so important that people have studied other methods, and there are methods that are constant factors faster than this. But certainly by comparison with insertion sort, this method solves our problem. It scales, and that's what we needed, is a scalable method so that as our company grows, we can grow with it, along with Moore's law. And so Alice says, okay, I'm ready to go now. I've got my whitelist generator.